If a formula or several formulas, as in this example, is used to define a function f, then we assume the domain of this function to be the set of all numbers, for which f of x is defined as the real numbers. Okay? Determining the natural domain of a function often amounts to excluding all numbers, say x, that result in dividing by 0 or in taking the square root of a negative number. Now let's proceed to the example. Find the domain and range of each of these functions. A, f of x is equal to 1 over x minus 3. B, g of t is equal to the square root of t minus 2. Solutions for letter A. Since the division by any number other than 0 is possible, the domain of f, this function, is the set of all numbers x such that the denominator, that is x minus 3, must not equal to 0. That is, x should not be equal to 3. Okay? So, the domain of this function, is all numbers. So, we denote the real numbers into a script R. So, all numbers except 3. Okay? Except 3. So, this is the domain for this function. And for the range, the range of this function f, is the set of all numbers y except 0. Since for any y not equal to 0, there is an x such that y is equal to 1 over x minus 3. In particular, x is equal to 3 plus 1 over y. So here, the range in letter A is all the numbers except 0. Because if you include 0, 1 divided 0 is undefined. Okay? So our range is all real number are except 0. 0 is not included. Okay? For letter B, since negative numbers do not have real square roots, thus the function g of t can be evaluated only when t minus 2 is greater than or equal to 0. So, the domain of G is the set of all numbers t such that t is greater than or equal to 2. So, the domain of this function g of t, is all numbers from close interval. So 2 is included starting from 2 to positive infinity. Okay. So this is our domain. Now for our range. The range of G of t is the set of all non-negative numbers. For y is non-negative, okay, is any such number. There is a t such that y is equal to the square root of t minus 2. Namely, t is equal to y squared plus 1. Okay, so our range here is r. Okay. And now we proceed to the functions used in economics. The demand function, denoted by d of x, for the commodity is the price P, which is equal to d of x, that must be charged for each unit of the commodity if x units are to be sold or demanded. Okay. The supply function S of x for the commodity is the unit price P equal to S of t at which producers are willing to supply X units to the market. The revenue R of X obtained from selling X units of the commodity is given by the product. This R of X is equal to the number of items sold, that is the X, and the price per unit, the P of X, okay? This is the price per unit. The cost function, C of X, is the cost of producing X units of the commodity. The profit function, P of X, is the profit obtained from selling X units of the commodity and is given by the difference of the revenue minus the cost. So our revenue is equal to R of X minus the cost function C of X, and the R of X is equal to X times P of X. Generally speaking, the higher the unit price, the fewer the number of units demanded, and vice versa. Conversely, an increase in unit price leads to an increase in the number of units supplied. Thus, the demand functions are typically decreasing, falling from left to right, okay, while supply functions are increasing, rising, as in this illustration.